Hey everybody. All right, so we've been having a little bit of a discussion about whether or not exposing high intensity light to a photomultiplier tube and the sodium iodide crystal will have any lasting effect after it's reassembled. Some folks have the opinion that we need to let these things settle down. So if it's been exposed to light for any period of time, you should let it expose. I've heard anything from between a few hours to, a week or even longer before you should hook these things up. Not that it's going to be damaging to them. It's just that there could be some residual photonic activity within the photomultiplier and the crystal, causing a difference in counts or something that would skew the numbers. So my opinion is, when it comes to amateur gamma spectroscopy using MCAs similar to PRA, Beckmani, or Thermino, it's not going to make any difference. Even a resolution difference of 1.5, 2, maybe even 2.5% is not going to make any difference with the radioisotopes that we as amateurs would normally run across, especially dealing with something that is based on an audio system, which is what PRA and Thermino and Beckmani use. So what I'm going to do, I'm going to take this thing apart. I'm going to take the crystal out. I'm going to expose it probably for maybe about a minute or two to directly to that light. And I'll probably even expose the PMT to that as well. I mean, I got a lot of PMTs. So as long as the PMT is not energized, okay, obviously exposing a PMT to light when it's energized would be devastating and it would essentially destroy it. But when it's not energized, there's going to be no amplification that's going to take place. So I'm going to expose the non-energized PMT directly to that light as well, which you'll see in a few moments. And then we're going to go ahead and reassemble this whole thing, pack it up, and hopefully within about 5 or 10 minutes, because that should be about as long as it's going to take me to reassemble this, I'm going to put it back in the lead castle and conduct a comparative analysis. So before I take this whole thing apart, let's go ahead and go to the PMT first. To the lead castle and do a first test before it's being exposed to light. And the reason why I'm going to do that now is because this PMT assembly was put together a little over 2 years ago. So it has been in a dark environment, completely almost unused. I think I've only ran a couple of specters on this in the time that I've had it. So it's been sitting in a shoebox, packed away in the dark for over 2 years. And so let's see what we've got first. So let's go over to the lead castle. Okay, so here we are at the lead castle, and here's the Hamamatsu PMT assembly. Its optimal range for gamma spectroscopy is 815 volts, and I've got it set for 815. And I've got the Thermino MCA set up. It's completely zeroed out. So we're going to let this run for 500 seconds and figure out what its average pulse per second is before I light this thing up with high intensity light. So as I pointed out before, this thing has been sealed up for probably about 2 years now. So it's been in extremely dark conditions. So let's go ahead and put this in the lead castle. And I don't have anything in the castle, so this is just going to be a bare run of nothing, just background. All right, and let's go ahead and hit start. And there we go. All right, let's see what these pulse per seconds do. I remember right, this thing is going to average probably around 4 pulses per second. All right, so we're just going to let this thing run for a while, and we'll be back at about 500 seconds. Okay, 500 seconds. That's 1,815 total pulses, and the average pulse per second is 3.6. Okay, so we're going to do one more test, and with this one, we're going to have a radium source, and we're going to go ahead and put this in the lead castle here with the detector. No need to really be all scientific about it, so I'll just drop it in there like that, put the cover on it, come back over here, and we'll go ahead and do another 500-second run on this, just for comparison, when we take this PMT apart and expose it to light, reassemble it, and see what we've got. Okay, you can already see the radium peaks showing up here. Let's go ahead and you got the radium peak here where the blue line is. You definitely see bismuth 214 here, and lead 214. The 3 peaks are going to line up perfectly. Let's see, where's the lead? There we go. All right, so that's all looking pretty normal. Bismuth 214. And let's go ahead and let this run for a little bit. It's currently at 44 seconds, so we'll be back at 500 seconds. Okay, here we are approaching 500 seconds. All right, so 500 seconds, average of 231.6 pulses per second with this radium test disc, with a total amount of pulses of 115,707. And that's what the spectra looks like, which is extremely classic for radium. So let's go into the shop and take apart this PMT and expose it to light and see what differences we've got. All right, so let's go ahead and start taking this apart. Okay. Okay, you can see the PMT here, and you can see that crystal is really nice. There's, which is not unexpected, because it really does give some good resolution, as you can tell with the spectroscopy test that I just conducted. All right, so what I'm going to do now is I'm going to clean this thing up. I'm going to take all the tape off, and then we're going to expose it to some light. Okay, so this is where I'm at so far. This has been pretty easy to take apart. There's not any major issue. As we all know, the standard way of putting these things together, it just involves a lot of black electrical tape. Some people put mu metal around these things when you might be in an environment where there's some electromagnetic concern, but again, those are going to be things if you're going to be doing some real high-end work, which I still have not really seen any of that have any direct effect on what we do as amateurs. Not saying I wouldn't use mu metal, but is it going to make a gigantic difference in what you do? Probably not. Okay, so there's the R580. And let's go ahead and set this thing up and expose it to some light. Okay, so here we go. I'm going to zap this with not just regular visible light, but I got a high intensity UV light here. So let's go ahead and expose that for a little bit. Okay. And we'll expose this. All right. And let's do the big test. Let's go ahead and turn this guy on. As you can see, that's very bright. It's blinding me. All right, here we go. I'm not going to let this sit super long because I'm a little concerned about the thermal issue. I don't want it to crack. So we'll go ahead and really expose this for a little bit. This is probably way more than enough just here. Okay. All right, that's fine. Let's go ahead and do the same thing with this. We'll get it all the way around. Saturate the light onto the PMT. And let's go right like that. All right. Major photonic immersion. I think this is going to be excellent for a test. I just don't think the difference is going to make anything that's going to result in significant issues with gamma spectroscopy on how it's set up, at least in my system. All right, that's probably good. Let's do one more with this. All right, let's go ahead and put this back together. Okay, I just applied some silicone coupling compound, of optical grade. Let's go ahead and put this together. There's really not much to putting these things together. It's just a matter of ensuring that you've got it tightly coupled and very where it's made where no light can get into the actual photomultiplier tube or into this area of the crystal. Okay. All right, so I'm going to start wrapping this thing up, and I'll resume the video after I'm about done with that. Okay, so I'm just about done. I'll probably put another coat up here just to be on the safe side, but it's just a matter of getting a couple of good wrappings around this bottom portion, just into the base material to keep light from coming in on this side. So I'll continue with that. And obviously when you wind these things up, it's just common sense to overlap by about 50%. That ensures that you're not going to have any issue with light getting between the wrappings. And you need to get into the base of the crystal housing as well. And then I think a total of 2 or 3 good overlapping windings with regular black electrical tape is all you need. And, you know, I'm just going to point out one thing. The electrical tape I'm using is nothing special. In fact, I'm almost positive this stuff came from Harbor Freight. So there's no need to go out and buy all this high-grade stuff. This is going to do the job just as well. You won't have any issues. Okay, I'm gonna get one more winding or wrapping over the coupling area. And that should do it. Okay. Let's go ahead and put the base back on. All right, so let's go take this to the lead castle and the MCA and see what difference we have. I don't think it's even been 10 minutes since we last illuminated this thing. Okay, we're back at the MCA. I just got everything cleared out. We're down to 0 pulses, pulse per second 0. Let's go ahead and hook this up. We're still at 815 volts. Okay, it's nice and good. Let's take out this radium source. Put that over here. Get this down into the well. Okay, so this first test is just going to be the background like we did first. So you can see what we got in the background. All right, so let's go ahead and hit run. Yeah, I'm not noticing much of a difference already. Okay, so we'll let this run and we'll get back to you at 500 seconds. Okay, we're getting up to 500 seconds. And oh, I stopped at 1 second early, but close enough. All right, pulse per second, 3.8. Total pulses is 1,882. All right, so let's try the same spectroscopy test. I'm going to put the radium test source in here in the same fashion. Just drop it like that. Put this shield on the top. Come back over here, and we'll start a new measure. Okay, and that's going to go pretty quick. And you can see the bismuth 214 already forming. You can see the lead peaks, the radium peaks. This is turning out very nice, pretty darn quick. All right, so we'll revisit this when we get to 500 seconds. Okay, approaching 500 seconds. There we are. Pulse per second, 346.3. Total pulses, 172,955. And one thing to keep in mind is the way the source is being dropped into the chamber. Positioning differences are going to make a slight amount of variance in the total count, but it should be close enough. As you can see, the resolution is almost identical, very, very minimal differences. So, all right, so let's back out of here and kind of examine what our differences are in the numbers. Okay, so the conclusion is this. Background before illumination was 3.6 pulses per second, and background after illumination and rewrapping was 3.8 pulses per second in 500 seconds, which made a grand difference of 0.2 pulses per second. The grand total in 500 seconds was 1,810 pulses, and the illuminated afterwards was 1,882, which made for a difference of 72 pulses per second. So that is somewhat close to the margin of error when you conduct these things, just on the basis of the uncertainty principle with decay patterns. I'm going to say it was just ever so slightly above what normal background would be. I will say that the normal background radiation in that chamber does generally fluctuate between 3.5 and 4.0 pulses per second over the year, depending on what year it is, what the radon content is, and what the atmospheric issues are. But it is generally between 3.5 and 4.0. When it came to the gamma spectra of the radium source, I did notice I had an issue when I dropped in the radium source. I should have been a little bit more scientific about it and actually placed it in there so the positioning could have been exactly the same each time I did it. So the very first time I put that in, when I removed the PMT assembly, I realized that the disc had stopped probably about a ½ inch above the crystal on the PMT assembly. It kind of wedged itself between the lead insulating material and kind of stopped there. So it wasn't directly against the crystal housing. And on the second time with the illuminated test, it fell completely to the bottom, right up against the crystal assembly, which gave it a much higher count. And so just for the purposes of discussion, the unlighted, where it stopped about a quarter or a ½ inch above, provided 231 pulses per second and had a grand total after 500 seconds of 114,559 pulses. The secondary illumination test resulted in 172,935 total pulses with 346 pulses per second. So that was a pulse per second difference of 115 and a grand total difference of 58,396. However, I don't believe that has anything to do with the illumination. It is definitely due to the distancing of the source. Maybe at a later time I'll reconduct that test. However, when you look at the resolution differences between the two gamma spectras of the radium source, the differences are negligible, the resolution is identical, and there is nothing really to write home about. So again, my conclusion on this is that for amateur, I stress that for amateur gamma spectroscopy, there is no reason to let your PMT and your crystal stabilize or just sit around in the dark for hours and hours and days or weeks. Okay, for what we do as amateurs, looking at radium and cesium and bismuth and different things like that, there's literally no reason you couldn't just immediately plug this thing in and go to work. It's not going to damage your PMT assembly, and you can automatically start using it. That's my opinion based upon what you've just seen. All right, there you have it, and looking forward to feedback on this one. It's a learning process, and if I'm wrong on something, point it out, and I'd like to see a different test that we can put together and maybe come up with a different sort of result. All right, take care. Okay, and just one last thing as a parting shot. This is a very small, low-yield lutetium-176 source, and it's at about 1100 seconds. But you can see the resolution is good. And this is, again, with the after-illuminated version of the PMT assembly. There is just nothing to complain about. So anyway, there you have it.